Was supposed to have clicked that. Okay, for those of you who are actually watching the recording, if there is anyone, we discussed one problem, and then I noticed that I hadn't started the recording, so I started the recording, and from now on the session is recorded. Unfortunately, the smart board refuses to turn on, and I am not sure how helpful this recording is going to be. Good luck listening to it. Okay, let me read the problem that you showed me.
Maybe it will turn off.
No, projectors usually do that when they're turning off.
Oh, so it'll turn off and then we can, I don't know, yeah. Maybe.
So let G be a graph. So let G be a graph with positive edge weights, WE for every edge E in the set of edges. And let F be a subset of the set of edges. And namely the set of edges with the smallest weight C. Okay. Do you know what that means?
Yes, I know what that means.
Okay, can you explain that to me?
There is some graph. There is a set of edges F where every edge contained in the set F has the smallest edge weight that we have in this graph.
Oh, so there could be many edges with the same weight, and that could be the smallest. All right.
Yeah, but F is not all of the edges with the smallest weight, is it? The set of edges with, okay, it is. F is all of the edges with this smallest weight. This number is C.
All right, so now prove.
No, not the number of edges is C, but the weight value is C.
So now prove that F is contained in every minimum spanning tree T of G, if and only if F is acyclic.
Okay. Well, so I did the first part. If we assume that there is this set F contained in a minimum spanning tree, F, if it is contained in a tree, cannot be a cycle because it cannot have a cycle in it. Because if it did, then if it would be contained in this graph that we think is a tree, then it wouldn't work out.
Okay, if F is contained to the tree, then it is acyclic. Now the harder part, if F is acyclic, yay, the maintenance light on the projector is flashing. Awesome.
Oh, that's why.
So it's not my fault.
That's why? Are you sure even if we...
So then, the harder part, if F is acyclic, then it is contained in the tree. So what have you learned about minimum spanning tree?
Well, let's say we have some F. Oh, it's acyclic. Okay. F is acyclic.
Right.
F is made up of trees.
Right.
Okay. Now, each of these trees, well, maybe we can, if we consider parts, if we consider parts of the graph and we localize, we look at each part more closely.
Okay. All right. You are focusing on the right. So you want to go and show that it's a tree. So it's contained in the minimum spanning tree. So I'll here start with what I know about F. It's the set of edges with minimum weights. and what I know about the minimum spanning tree. So that I'm actually not sure. I mean, I know things about the minimum spanning tree, but what have you learned about them?
Oh, about minimum spanning tree?
Yes,
They're connected?
they're connected. Any other tree that spans the graph has a sum of weights on its edges at least as large as that of the minimum spanning tree.
Okay.
It can be generated with Prim's and Kruskal's algorithm. And
Okay, that's where I start getting fuzzy.
So
is it about Prim's and some algorithms?
Oh, I mean that problem in particular.
Any graph that is acyclic
Yes.
is made up of trees.
Yes.
Components of the graph are trees.
Right.
So the components, so we can say that some f has some components and they are trees.
All right. Okay.
So if f is made up of all of these tree components, there's a graph G, which f is a subset of. Well, first, if we try to disprove it, how would we try to disprove it? If we could draw some tree components and then say that somehow the minimum spanning tree does not include these, but these, they're all
Right.
They're all C though.
Right. So let's draw our minimum spanning tree.
I think maybe contradiction could be the way to go. What, minimum spanning tree?
Right. We can draw the minimum spanning tree, and let's say f is not contained in there, so there is an edge in f that is not in the minimum spanning tree. All right. So it's still.
Do we know that the minimum spanning tree has to use like all the minimum edges or something?
I don't know if you do.
Is that a theorem?
It is Kruskal's algorithm. Further Kruskal's algorithm.
Oh, so it's sort of like a theorem. I just would have read this, but it didn't have time. Sorry.
Okay.
So can you explain Kruskal's algorithm?
I mean, all right.
Okay, just go on. Say what you want to say.
Okay, so simply the contrary that we have our minimum spanning tree here, and we have an edge that is not part of the minimum spanning tree, but that edge is in F.
Therefore, its edge weight is C, which is the minimum edge weight.
Right. So now this edge connects to vertices of the graph. And there is also a path along the tree that also connects those two vertices in the graph because it's a spanning tree.
Right, okay.
Now,
and the spanning tree does not include that.
Now, suppose all these edges are of weight C. Then,
which is the minimum possible weight they can be.
Yes. Then we have a cycle in F.
Ah.
That's a problem. Because we are starting with
Oh,
is a cycle. Suppose
So one of them is C plus 1.
so one of them is C plus. Now let's delete it and add that one.
Oh. And now you have to prove that we can replace it like that and it would work.
Now, the resulting is still a spanning tree because those two vertices neighboring the edge we removed are still connected. This time they're connected through C because
because together they would make a cycle, and with any cycle, if you delete one edge, it's a path.
However, the weight of this new spanning tree is less. Therefore, this could not possibly have been our minimum spanning tree.
Okay. That's it?
That proves the problem, which actually brings us to Kruskal's algorithm.
Proves the what?
Proves what we wanted to prove.
Yeah, we got that answer.
Yeah.
Okay. Yeah.
Now, which brings us to Kruskal's algorithm. We have some graph.
Okay.
2, 3,
Complete
5, 4, 8, 7, 6, 1. And we want to make a minimum spanning tree. What we do? We take the smallest edge. 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 Now, this is smaller, but we don't take it because these are already connected.
If we did take it, then we would have to disconnect 2 or 3, which would be really bad.
Right. So at each step, we take the smallest edge whose endpoints are not already connected until we take n-1 edges. And the result is the minimum spanning tree. The proof is slightly generalized version of it is exactly this. However, we don't know that this is C. We just know that assuming that the minimum edge is not part of the spanning tree, we can reduce it. Therefore, the minimum edge that is
assuming the minimum edge is not part of the spanning tree.
Here we have added some edges, and now we've added 1, we've added 2, and here we're adding 3. So we can assume that this edge is not part of the minimum spanning tree. Do this again, show that this edge is part of the minimum spanning tree, and add it to the minimum spanning tree. That is essentially what Kruskal's algorithm does.
Mm-hmm. So with Kruskal's algorithm, why couldn't we have just said, if Kruskal's algorithm says that using the algorithm definitely gives you a spanning tree on any graph, doesn't matter if it's 1, 2, 3, 4, 5 or 1, 1, 1, 2, 3, 3, 3, 3, 7, 7, 7, 6, 6. You know what I mean?
Okay.
Does it not matter?
Yeah,
if we change, for example, you give me an example where this edge weight is 1, this one is 2, this one is 3. In an example where we have multiple edge weights that are the same, would it work as well?
Yeah.
Okay.
And every step I take one.
Yeah.
One of the edges with the smallest weight that don't connect vertices that are already connected. And if there are multiple of them, I can take either.
So if f is acyclic, then we could have just said that all we need to do is apply Kruskal's algorithm, and we'll see that it has to find f.
Yes.
Okay.
Now, I'm actually guessing that you at least would be expected to actually write this proof I outlined here on the exam. Because
and not invoke Kruskal's algorithm?
Oh, probably, at least if it's one of the proof problems.
Yeah, it is. Okay.
If it is one of the previous problems, then you can invoke the cross argument. All right. So, hi, Rich. Can you hear me? All right. So,
Maybe he can't talk.
yeah, he chats.
Oh, he can't. He doesn't have a microphone.
All right. So, do you have any questions you want to ask? No, just listening. Okay. We have a technical problem with the smart board, but we'll try to discuss things in a way that you can listen into. So,
Let's see.
all right, let's move on to the next problem.
Okay.
Do you have the practice exam?
We're on the practice exam from 2005, and I'm gonna try the last problem, the very last problem of the practice exam from 2005. So I'll read it here. Prove that a tree T has a perfect matching if O of T minus V equals 1, meaning the number of components of T minus V equals 1 for any V that's in the vertices of T. So the number of odd components, there's only one odd component.
Can I?
Okay.
Also look at that. Oh.
Well, for a tree to have a perfect matching,
All right, come over here though.
if a tree has a perfect matching, if a tree has a perfect matching,
Wait, where's the problem?
last page.
Right
There.
Prove
That's the beginning of the problem, and then you read here.
So prove that a tree T has a perfect matching if O of T minus V
So first, assume that tree T has a perfect matching. If it has a perfect matching, it must have an even number of vertices, because each perfect matching, each what do you call it? Each match, each edge in the perfect matching would give us 2 vertices. Tutt's theorem, maybe. What's Tutt's theorem? Let's see. Tutt's theorem. He's really on top of things, I think. Definitely more than I am. Where's Tutt's theorem?
It is the theorem that tells you when. Oh no, I was thinking.
Tutt's theorem. Do you want to tell us where to? Oh, a graph G has a perfect matching if and only if for every subset of the vertices. For every subset of the vertices, the subgraph induced by removing. Okay, so the subset induced by removing any subset of the vertices has at most that number, meaning the number of vertices in that subset, that number of connected components with an odd number of vertices. Ooh, wow. Okay. Okay, that's deep.
So I still haven't. So prove that a tree has a perfect matching if what's that?
A number of odd components. Okay.
Number of odd
components. So again, we start with a T. He's telling us something.
Okay.
Okay, we got it. We looked at it on Wikipedia. 3. Oh, if it's in chapter 3, we can't use it, right?
Well, if it's in chapter 3,
Because we're on chapter 2.
probably Alice will. I mean, I don't know what Alice will do if it's in chapter 3. I'd expect you can't use it, but
Yes, yes. This is not about learning and understanding. This is about the test.
You actually are already in chapter 3. You're just.
Yeah, we're actually in chapter 4.
But you're just now doing the test on chapter 2? Okay.
Yeah.
I'm pretty sure I saw Hall's theorem, though, on one of the previous exams.
Okay. What chapter is that in?
It is very similar to Tift's theorem, and it is not clear that the exam 2 in 2005 was also not including chapter 2. So it's entirely possible that in this problem, it's using Tift's theorem is okay, or Tift's theorem.
Is okay?
Yeah.
Oh.
I mean, one of the other past exams had a problem that was like, what does Hall's theorem state? Which I'm pretty sure is also from chapter 3.
Maybe then they had done chapter 3.
Yeah, that's what I'm saying.
But now we have not done we're not doing chapter 3.
Probably.
But let's do it. Maybe if we do it without Tut's theorem, we'll. Oh, maybe not you. Maybe you know more than I do. But I don't know. I was thinking maybe I'd learn something if I did it. Or we can go into a different problem. Sorry.
I mean, it's up to you guys.
I would do it. I would try to do it if I can.
You want to do it?
Well, Rich seems to not. I mean, he's just listening in. So.
All right. So
I just want to do this because for everything else we have the answers. Okay. So, prove that a tree has a perfect match. Let's assume we have some tree with a perfect matching. Any tree with a perfect matching has to have an even number of vertices. Now, what else?
Wait, a tree?
Yeah. A tree can have a perfect matching.
Well, that one doesn't. Okay.
Like this.
Oh, yeah, that one.
Okay, like this and like this, for example.
Right.
Okay.
Okay.
So, but it doesn't have to.
Yes.
Here, for example, does any tree with an even number of vertices have a perfect matching?
No.
No?
No.
Let's give an example. Okay.
Yes.
Good. Great. So now it does have an even number of vertices. Oh, maybe I should do it here. That's an example of a tree with an even number of vertices that does not have a perfect matching. Okay, so let me do it here. First of all, T for some K. Okay, so now our question is about the number of odd components of T minus V. For some vertex. Oh, I see. So, for example, when we look at this example, we see if we delete that, yeah, we have 3 odd components. Not odd components, but yeah, 3 odd components.
Right.
So if it only makes 1 odd component, well, again, an odd component means that the number of vertices in the component is odd, that's all?
Yes.
Okay. So
it also means that the number of edges is even, 1 less.
Right.
So
well, let's look at an example. Let's say that some tree has a perfect matching. And when we delete a vertex, let's say some tree, if we delete a vertex from some tree, then we get only even components. Let me see, what? Here?
No,
No. Where? Here?
the Chrome. Yeah.
Okay. What? Sorry.
What edge in the matching is adjacent to V?
V is any vertex.
Right.
So if we have a tree with a perfect matching, there's some perfect matching in the tree. For any vertex V, when we delete it, the number of odd components should be 1.
Right.
That's what we
And
want.
so, as Rich was pointing out, it is useful to look at the edge that is in the matching that is adjacent to V. Like you have this vertex V, and it's going to be matched to some other vertex because there is a matching.
Yeah, okay.
And it can have other edges that are not adjacent. I mean, that are adjacent to V, but are not part of the matching.
Okay. That they can't be part of the matching.
Right. So, do you see?
Oh, I see. So if we have a tree, then any edge is a cut edge. So when we delete some vertex, of course, we're going to cut that edge and make at least 2 components. We're going to make, we are going to make the number of components equal to the degree of that edge, of that vertex. Right. Okay.
Now,
good. So now, what?
Go ahead.
Okay. I'm sorry. I'm just slow. This is gonna take me some time, maybe 2 minutes. I don't know. So now, looking at the diagram, if V was an edge, and it had, if V was a vertex that obviously was part of an edge, then deleting V okay, we have V and V prime. V prime is the vertex that was adjacent to V in the matching. Let's say, case 1, V prime was a leaf. If V prime was a leaf, then V prime by itself becomes an odd component when we delete V. What happens to everything else? If we consider the rest of the graph, aside from V and V prime, whatever the rest of the graph is, that has an even number of vertices. Now, I see. There's some induction or something here.
No,
because
I mean, in this direction there is no induction. You just say each of those components are already perfectly matched. So each of those components have even number of vertices. And
okay, could you explain more exactly what you mean? Each of those components are already evenly matched.
There exists a perfect matching.
And it couldn't, and for any of these vertices, it couldn't have utilized V. So they must match with something.
Yeah, I mean,
something else, etc.
You have this vertex V, and it is matched to this vertex V prime. Now, if you remove the vertex V, all other edges of the matching, except the one that connects V and V prime, would stay there. V and V prime would be disconnected. These edges of the matching would disappear. So V prime will now be lonely. Everything else would still be perfectly matched. So the vertices in this component would contain a perfect matching. It's only going to be within the component because it's the whole component. And so this component has an even number of vertices.
Okay.
The same is true for this
Okay,
component.
Okay,
And
we got it.
in this component, the vertices except V prime are still evenly matched, but V prime is lonely, so this one has.
Oh, you're not even doing the case one like I was thinking of with a leaf. Okay.
Yeah.
Okay. So that's it?
That's it for this direction.
Okay. The opposite direction, I think it was easier. So let's assume that a tree T has a perfect. So assume we have a tree T, and when we remove any vertex from the tree, the number of odd components becomes exactly 1. Well, I don't understand. This tree does not have a perfect matching.
Okay.
However, when I remove this vertex, the number of odd components is 1.
Yes.
I'm talking about this tree.
Right.
So I think that's a contradiction.
A way to rephrase the problem would be a tree contains a perfect matching if it is true that for every vertex, removing that vertex leaves us with exactly one odd component.
No, but we're doing backwards. We're going the other way. So
So
when we look at this tree that we drew, I don't see how it can be true.
Okay, so now you have a tree. What you know for this tree is that whichever vertex you remove, you'll be left with exactly one odd component. You want to prove that there exists a perfect matching.
But look at our contradiction.
Yes, in this tree, if you remove the middle vertex, you're left with 3 odd components. You know that for every vertex. For every single one.
I see.
You're left with exactly one odd component.
Okay. Okay. Interesting. Well, any vertex I remove from the tree gives me only one odd component, exactly 1.
Right.
The contrapositive would be that if there is no perfect matching in the tree, then
There exists a vertex
that you will remove and get not one odd component, but either 0 or many.
Yes.
Okay, can we go that route maybe?
I don't know. We can try to go that route.
Okay.
So
let's say we have a T where, okay, so a T without a perfect matching. A T without a perfect matching, what does that mean?
It means there is always a lonely vertex. But frankly, I, I can't go on from here either. But what I could do is is not go into contrapositive because I'm exactly stuck in the exact same place where you're stuck. No perfect matching doesn't really give me anything. But instead, I can try to come up with a way to use that property and come up with the matching.
Well, any vertex you delete will give you exactly one odd component.
Right.
That means, that means that every vertex is part of a matching. Why? Because if there were a vertex that would not be part of a matching, i.e., if there would not be a perfect matching, then when you delete this vertex, you get something. Wait, let's think about it.
So which
Try
says
constructing a matching and show it's perfect.
oh yeah, constructing
Just drawing a matching.
yeah, constructing a perfect matching here is indeed, I'd say, the way to go. But your idea doesn't necessarily prove itself unworkable. The problem we see there is assuming that property holds, you're saying that every vertex is part of a matching. Because if a vertex isn't part of the matching, and then you remove it, you're saying that everything else is perfectly matched.
Not necessarily.
But yes, but not necessarily, because there could be another vertex that also isn't part of a match.
Oh, so either everything else is perfectly matched, which means that everything else is an even component, and we only have even components, which means there are zero odd components.
Right.
Or everything else is not perfectly matched, which means we have more vertices which are not part of a perfect matching, which are not part of a matching.
Right.
Which are, how do you, which are not, some of which would not be part of any matching.
Exactly.
Yeah.
Which is well, I'm stuck on this case. But all right, the fact that we know that the property holds for every vertex means that we can pick some vertex that has some awesome nice property and other awesome property, and what we know would still hold there. Give me some vertex that is special for a tree.
Leaf.
Leaf. Okay, so we have a tree, and of the tree we have a leaf. Now, removing.
Technically, is a leaf an edge or a vertex?
The leaf is the vertex.
The vertex, okay.
So removing that leaf leaves us with exactly one component. And we also know that it is an odd component. Now.
Okay, so we're starting with if removing a leaf gives you an odd component.
Oh, I mean, you know that removing a leaf gives you an odd component because it gives you one odd component. And it gives you one component, so it has to be odd.
I would say all we know is that it has to have an even number of vertices, which is good. We know the graph. We know the tree now has an even number of vertices, right?
I mean,
because we removed one vertex and got an odd component.
Right.
Okay.
So it hasn't even. But I would actually go and do something slightly more sophisticated. That is my tree. That is my leaf. I will remove this vertex.
So a vertex that's adjacent to a leaf.
Yes, vertex that's adjacent to a leaf. That would give me one odd component.
That means that all the other components are even.
And yeah, a bunch of even components. Now, I will connect this edge, this leaf to this vertex.
That's part of the matching.
As part of the matching. And then I will recursively apply the same procedure to all these components.
All those even components. Okay.
Now, what's left to show is that the property still holds there. It will hold pretty much everywhere, except possibly here, because that vertex changes. So if we removed that vertex originally, we would have had exactly one odd component. But now this vertex looks a bit differently, so we need to verify that this is still true. If we removed this vertex originally, we'd get that component, and this component.
Yeah.
And this component is an even one, that large one here. Because this is even component, this is even component, and these are two vertices. So the odd component.
Okay.
So the odd component has to be one of those two.
Okay.
Therefore, just looking.
One of those, you don't know that it's two.
One of those, yeah. Therefore, just looking at this graph, removing this vertex still gives me exactly one odd component.
Because you know there has to be a perfect matching in that graph, and we already proved the forward direction.
I mean, no, because I know that in the whole graph, removing this vertex gives me exactly one odd component, and I know that this component that is not part of the subgraph I'm interested in is even. Goes even, and 2.
Okay.
So the odd component has to still be here.
Okay.
So now I know that in here, once the property that removing every vertex gives me one odd component still holds. And so I can inductively or recursively say there's a perfect matching there.
Okay, I sort of get it.
Now, the base case of the induction would be to this tree, which happens to have a perfect matching.
To what tree? The tree that happens when you take away the...
No, I mean, I need to have some base case for the induction. Mm-hmm. And my base case is going to be this.
C2, right?
No,
K2.
K2, right.
Okay.
And K2 happens to have a perfect matching. So
Yeah,
my best case is fine.
okay. Can you explain it again, please?
Can I explain it again? I can.
Maybe I should try.
I'd rather not do it on that, but okay. So we have a tree and we have a leaf in the tree. Every tree has a leaf. So removing this vertex gives us exactly one odd component. That has to be the leaf. Thus, all other components that are generated by removing this vertex are even. So, what I can do is connect this vertex to its leaf and recursively make perfect matchings in these subcomponents.
Because each of those components are even.
Now,
right? Each of those components are even. Yeah.
However, I mean, the fact that each of those components are even doesn't let me recursively, because it's a different property. I mean, to recursively do it, I need to show that the same property still holds in each of those components. That is, removing a vertex gives me exactly one odd component. So, without loss of generality, consider this component. It has a vertex here, and that is connected to stuff. Now, I know that for all of these vertices, I know that removing that vertex gives me exactly one odd component in the original graph. Mm-hmm. Or I'm removing any vertex here gives me exactly one odd component in the original graph. And I need to prove that it is still true internally within this component.
Mm-hmm. Mm-hmm. So let me think. Okay. Well, within this component, can't you just consider a vertex that's near a leaf? You would get the same thing?
Yes, but I first need to show that the property, if you delete here, in the original graph you have a property. Now I need to show that if I delete everything but this component, my property still holds. Because if it doesn't, then I can no longer.
Okay, everything except this component had an even number of vertices. Therefore, the component also has an even number of vertices. The component is part of the larger tree. Therefore, when you would delete a vertex that's near near a leaf, then in the larger tree, the property would hold. And in the smaller tree, it must also have, no, it must, well, the vertex which would be the leaf, that would be the odd vertex, and the odd component, and everything else would be the even component. Even minus even is even.
It is.
And is that it?
Well, I mean, you can't limit just yourself just to vertices near an edge. You have to say that the same property that originally held still holds. That is, removing any vertex gives exactly one odd component. But this component here that we removed, I mean, it was this and leaf.
That was an even component.
This is an even component, so removing it doesn't change any parities.
Mm-hmm.
Like, if we remove this vertex, its odd component is some other of the components that generate.
I see.
If we remove this vertex, no parities get changed because, okay, one of the components that is left after removing this vertex, it loses a huge chunk of it, but that huge chunk was even.
Take the edge UV between V and the odd component in T minus V. The edge UV between V and the odd component in T minus V. Okay. Let's show that U must be matched to V using the same criteria.
Well, here you have presenter rights reach, so you can go on the plus in the upright corner and show stuff on the screen. Because I wasn't sure what was U and V you were talking about. Yes, I hate that too.
What? What just happened?
It clicked erase and it cleared off screen.
Yeah.
Yeah, I hate that too. That's why I ended up using a different drawing app than this one. that edge between U and V is uniquely determined. I guess
I have to take 5 minutes and pray.
okay. I'll draw the same.
I'll be back in 5 minutes.
I'll draw the same thing Rich drawing.
I mean, you guys could go and do something else.
Yeah, I guess we
Come
can.
back. If Rich doesn't have any questions, whatever. Maybe Rich does have some.
Okay, so Daniel is leaving us for 7 minutes, so we can do whatever else in those 7 minutes. You're saying the edge UV must go from V to the odd component of T minus V, and must go from U to the odd component of T minus U. Okay, and those two edges happen to be, I'm guessing the U and V is the neighbor of U in the odd component after removing Q, and vice versa, V is the neighbor of U is the neighbor of V in the odd component after removing V. And so the edge between U and V is uniquely determined. Okay, that's pretty much the same thing that me and Daniel were talking about, except you take general U and V rather than one of them being a leaf to simplify things. It works, but you're stuck with the same problem that you now need to show that the same property still holds after you connect U and V and remove them. You're left with a bunch of other stuff, and you need to show that the same property still holds so that you can use induction. Every vertex is mapped to a unique adjacent vertex. Okay, that works.
What? Hmm.
That his idea is better than what I was suggesting.
Show that U must be vegetable. Oh, I thought there was an edge between U and V is uniquely determined. The UV edge must go from V to the odd component of T minus V, and must go from U to the odd component of T minus U. I don't think so. Um, okay. So every vertex. Oh, I see. Wow. Okay.
Yeah, that's good.
I think it's good. Let me see.
It's certainly better than what I was
That's
suggesting.
very easy,
Much,
yeah.
much easier.
So whichever vertex we delete, if it only makes one odd component, then it must have been matched to the vertex that is in the odd component, and there's only one. It only has and this vertex only has one edge with the odd component because each edge is a cut edge, right?
Right.
Right. Okay. And now, that's it. Now, if we do that for every vertex, that shows that every vertex is matched to some other vertex.
Right. And that's symmetric. So if U is matched to V, V gets matched to U, and every vertex gets matched, so it's perfect matching.
Mm-hmm.
Right. So what should we move on to?
Richard, you're awesome. Okay. Well. So for some of these, I don't see the drawing. I don't think he gave a drawing of the graphs he refers to.
I'm just writing an email to my bosses to tell them that this doesn't work.
Okay.
So, and feel free to.
It's okay. Write your email.
I mean, I'll write it in between other steps though. Just speak whatever you want.
Keep writing. When we had a physics exam review, the dude did not use the smartboard or any of this stuff.
Yeah, it's not every time.
Only for what?
Only when this is supposed to be streamed and available online.
Why?
Because
it's on Sunday?
No, I mean it's just.
Why wasn't the physics one supposed to be streamed and available?
Ask Hassan or Tayyab.
Okay. I don't care. I don't care that
probably
much.
There was some problem there.
I don't care that much.
I mean, generally they are streamed and available online, but occasionally something pops up that prevents that from happening.
Okay. Let's not do any of these simple ones. See, I don't have the graph.
Oh. Use any methods listed to determine the number of spanning trees in the following graph. Briefly explain any fact that you use, but you don't have to prove it. Okay. So yes, you don't have any graph.
Are you looking at do you have the site there? So this is that exam, right?
Right.
Okay. Can you go all the way down, maybe? Maybe there's something. No. Okay. Do you know what a Hungarian algorithm is?
Hungarian algorithm, yes, but I've kind of forgotten, so I need to look it up. It was for a weighted perfect matching, but if you have weights and you want the best perfect matching. Okay, so
Okay. This graph looks like this, right?
this graph, yes.
Just making sure I know what I'm talking about.
There's also weights on the edges.
Right. So,
Well, that's
10,
strange that you have. Oh, no.
Four.
Sorry, my bad.
6, right?
My bad. No. It's bipartite.
Why?
Hungarian algorithm works on bipartite. So it's K55 rather than K5.
Oh. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Well, if it's a K55 and we want a maximum weight matching, I would probably just take each heaviest edge each time.
No, the convention is you want minimum weight matching, but
No, it says to find a maximum weight matching.
oh, in that problem it's maximum. Oh, but taking the maximum edge each time isn't good enough.
I think it is in a K55. Yeah, I think it is.
No. How about this? Okay, here.
So I think we would take this one. Take this one. Take this one.
Okay, Daniel, see
Yeah.
see here, and
Yeah. What?
this graph, everything else is 1, or like let's say everything else is 0.
Oh, I see. I see. I see. If you take the 101, you won't get. Okay. Okay.
Hence the Hungarian algorithm to solve the problem.
So stupid. I didn't really prepare for this review session. Hungarian algorithm. Where is it? Page 126. 126. We're not going to be tested on this.
Okay.
We're not going to be tested on.
I mean, that is also a pretty complex thing to do now.
Is this actually on page 126 or no? Oh, here we go. Okay. We're not going to have to do this. So I think,
Yeah.
for me, I would just spend my time on something else. Okay. Give an example of a simple graph for which vertex connectivity is less than minimum degree.
How do you define connectivity?
Vertex connectivity means when the vertex connectivity is P, that means that the least amount of vertices you can delete to make it a disconnected graph is P. That means there exists P vertices that you can delete to make it a disconnected graph. And you cannot make it a disconnected graph by deleting P minus 1 vertices.
Okay, so the smallest number of vertices you need to delete to make it disconnected, and you want this to be smaller than the minimum degree.
Yeah.
Oh, okay. I mean, which here says smallest separating set. Oh, he's answering my question. All right, so
What was your question?
what's vertex connectivity? And
Smallest separate, yeah, that's what I
Yeah.
said, except he knows the terms.
right. So an example that is small. Any ideas?
Well, if we talk about minimum, let's just look here. If we talk about minimum degree 2, then we want vertex connectivity 1. Oh, well, I can show you vertex connectivity 0. I don't know if it's cheating. Yeah, I mean, if we have this graph, this graph has vertex connectivity 0, while the minimum degree is 1.
Right.
Maybe that's stupid, but okay. If it has to be a connected graph, which would make sense. Let's say we have minimum degree 2 and vertex connectivity 1. Is that possible?
Yeah.
I don't think so.
Sure it is. Think about it. Right, let's start with, we want some vertex.
There's no, there are no leaps
Right.
at all.
Right.
So everything is in a cycle. I think.
Yes.
So how can vertex connectivity
Okay,
be
so
1?
let's start with the vertex. I want this to be the separating vertex, and it's going to have at least 2 components. Now let's make them.
Oh, I see. Oh, okay. Oh, I see. Yeah, I somehow wasn't thinking of it.
Let's see. Yeah.
Yeah. Why did I think everything was in a cycle? I don't know. Okay. Yeah, that looks okay.
So here, and you can actually make the minimum degree as large as you want. Like you can make it 3.
Right.
But
Okay. I got it. Okay. A minimum edge cut. Once again, an edge cut is where we have a graph.
so you want the minimum edge cut for which the size of S is greater than or equal to 2.
Simple graph in which there is a minimum edge cut for which the size of S. Yeah, because the edge cut here cannot be just one edge.
I mean, I'd actually point here.
Need to look up the definition of edge cut. I don't think this is in chapter 2. This is not in chapter 2. Maybe that's why the 2005 exam is not so important.
Probably. It is kind of odd.
There was a graph theorist named Floyd.
No, I think the minimum edge cut, they mean a
Yeah,
cut
this is in
that
chapter 4.
has minimum edges.
An edge cut is an edge set of the form S complement, where S is a non-empty proper subset of the vertices.
Yeah.
Okay. An edge set of the form S complement. That's it. That's just the definition.
I mean, yeah, it's a set of edges that if you remove them, you separate the graph.
We write S comma T for the set of edges having one endpoint in S and the other in T. Huh. Can do.
Here. Yeah.
I see. This is sort of like imposing a bipartition on a subset on a subgraph, something like that.
Okay, which left, and it's already 8:06.
6 what?
And 6 minutes past 8.
Oh, okay. It's okay. We don't need this.